Hi everyone, and welcome to this video that is about one of the questions from the assignment that I gave you about Kc and Kp calculations. In this question we were looking at the equilibrium between sulfur dioxide and oxygen in equilibrium with sulfur trioxide. Okay, this is a very famous equilibrium reaction. It comes up quite a lot in exam questions, and the reason is because this reaction is used to produce sulfur trioxide that is then used in the manufacture of sulfuric acid in industry. It's called the contact process, and it is said that the industrial worth of a country can be measured by the number of kilograms of sulfuric acid it produces every year, because it's such an important industrial chemical. But back to the actual calculations in the question. The first part of the question asks you to write an expression for Kc and come out with a numerical answer, and you should have been able to do that using the initial change equilibrium method to find how many moles there were at the start, initial, how many moles there were at equilibrium, and thinking about the change in each of the different numbers of moles. Now, if you'd done that correctly, you would have got the answer 57.6. And the units of this are moles to the -1 dm to the 3. In various mark schemes, it has those two units the other way round. It doesn't matter. It really doesn't matter which way round you put them. Okay? So this is the answer. But the problem that people have now got is with the second part of the question, where you're now trying to articulate in words your understanding of this. So let me be very, very clear about what Kc tells you. We'll say a few chemical things about it. First off, look, it's a very big number. It's much bigger than 1. So the equilibrium is predominantly over to the right-hand side, and there's not much of these two chemicals in the equilibrium mixture. It's mostly going to be sulfur trioxide. And this is like a ratio. The ratio of this number compared to the ratio of this number, they're in this ratio, 57.6. And this number will not change, okay? It is not affected by change in many of the conditions that we could impose on it. So say we add some more, which chemical? Sulfur dioxide. We add more sulfur dioxide. As a result, this number would get bigger, and the calculation would no longer give this as an answer, but the equilibrium would shuffle going over to the right until once again the ratio of the two numbers went back to this. The numbers wouldn't be the same, but the ratio would be the same. Equally, maybe if I increase the pressure. See, increasing the pressure, good old Le Chatelier would tell us if you increase the pressure, the equilibrium moves over to that side because there are fewer number of gaseous moles. Yet when you put the numbers in again at the new higher pressure, the ratio between the two would be 57.6. So the value of Kc at equilibrium, it never changes. The only one factor that can change it is temperature. So if I vary the temperature, is temperature affects this value. So now we're armed with this information that Kc at equilibrium does not change according to pressure or concentration or the number of moles of the things in the equilibrium. In the end, the whole system shuffles until that number is the number for Kc when you substitute in. But if you change the temperature, this number will change. And this is the heart of the question now we're being asked. So let's just explore the problem in the exam question. So in one of the later parts of the question, it asks about Kc and what happens to it as temperature increases. Now we're being told in this story that as the temperature increases, that the value of Kc gets smaller. So Kc gets smaller in magnitude. The number goes less than 57.6. So what does that tell us about this equilibrium? Well, if Kc is effectively the ratio of the concentration of the products divided by the concentration of the reactants, would you not say that if this number is getting smaller, that is because the top of the fraction is getting smaller and the bottom of the fraction is getting bigger? Think about fractions. That number's getting smaller, this number's getting bigger. If you put that in the calculator, this number would get smaller. So therefore, the equilibrium is going that way. The products are becoming less and less, and the reactants are becoming more and more. Temperature increase is making the equilibrium shift to the left. So what must be true about this equilibrium? It must be exothermic. It has a negative delta H. Think back to Le Chatelier. If the forward reaction is exothermic, increasing the temperature causes it to move in the endothermic direction, so that will be back again. Now we can work out that it was a negative number for the delta H because we're told the information that as the temperature increased, the Kc got smaller. Now the very last bit of this question is difficult to see because the question is asking you to talk about the situation in terms of Kc. So we're being told in the situation that the chemist repeated this experiment, and instead of using 1 mole of sulfur dioxide and half a mole of oxygen, she decided to use 1 mole of sulfur dioxide and an excess of oxygen. But she did the experiment under the same conditions, under the same temperature. So therefore, if temperature doesn't change, Kc does not change. It is still that number. Now, if there is a lot more of this, then surely, by definition, this number here is going to be much bigger than it was in the first expression. And yet the numerical answer is still the same. Well, if the bottom of the fraction is becoming much bigger, and yet the answer is still numerically the same, then surely, by definition, this number must also be bigger. It must be bigger, otherwise the final numerical answer would not work out to be that number anymore. It would be much smaller, because the bottom of the fraction has got much bigger. If you're dividing by a bigger number, you'd end up with a smaller answer. Well, but you can't end up with a smaller answer because Kc is only affected by a change in temperature, not by a change in any other condition. So at a constant temperature, I must end up, when I put the numbers in my calculator, with 57.6. Therefore, if that number got bigger, I got bigger as well. So come back out of the mathematics and back into the chemistry. What does this imply about the equilibrium yield of sulfur trioxide? This guy, well, I would get a bigger yield. Now, Le Chatelier would lead us to the same answer. Le Chatelier would say if you added more oxygen to the equilibrium mixture, it would push the equilibrium over to the right to decrease the amount of oxygen. That's all very good, but Le Chatelier is not the answer to this question, because the question asked you to make an argument based on Kc. And if you noticed, I made the argument based on the fact that Kc only varies with temperature. At a constant temperature, it gives a constant numerical answer. And that is how I would word the answer to this question. Now, what you might want to do is watch this video, go back to the question and look at the mark scheme and see if now the mark scheme makes sense to you. And once you've seen the mark scheme and it's made sense to you, go back to the question and write this again in your own words to allow the thinking to clarify in your head. Okay? And as always, I'm just at the other end of the internet if you need any help.